It's a simulation model of the Arctic Ocean with ice and ocean coupled together. We're funded by BOEM, the Bureau of Ocean and Energy Management. They're interested in what the surface currents are and the surface winds and surface ice motion, and they take those three fields together and they produce maps of where oil would go in the event of an oil spill.
Lots of ice coming.
In the summer, the blue there is the open water, and the gray, the light gray, is at least 90% ice cover. And so every summer you get some of the ice retreating, melting away, and then in the fall it grows back. And the exact position of where the ice edge is isn't quite right, but we have roughly the right amount of ice, and that's dominated by the thermal forcing, which comes from that atmospheric model that we're using. And so we're confident that we're getting about the right amount of heat coming into the system and leaving the system.
The ice is really difficult to get, especially in the Arctic, the multi-year ice. In the Bering Sea, the ice is reset to zero every single year, so you can start growing ice in the fall in a fairly realistic fashion. But if you have ice in the Arctic, which doesn't go away every year, if you have an offset one year, that could grow and influence your results for the following year and the year after that. So it's a more difficult beast to get the ice right in the Arctic.
Another thing we've done in this particular simulation is we've added a land-fast ice component, and we're using data from Andy Mahoney. Andy Mahoney did his thesis studying the land-fast ice of the Alaska Beaufort Sea. It's a place where every winter land-fast ice is generated and then breaks up and floats away come summer. And so the timing of that is of interest to the native communities, because there have been people who've been out on the land-fast ice and then a huge chunk of it just breaks away and they're floating away and they have to be rescued. And the behavior of that, I think, has changed over the decades.
I don't know the internal dynamics of ice probably as well as she does, but the character of the ice can change with thickness and with temperature. You have to get a lot of other things right to get the ice close to right.
The next phase, if we were to do more work on this project, would be to learn how to create an ice model that could be run in a limited domain. We've been doing that for years with the ocean, and using boundary conditions from larger ocean models, we can make a pretty good small regional ocean model that doesn't have a lot of boundary effects. But in the ice model, I described earlier that I was having all kinds of trouble with the ice edge being either too stiff or not stiff enough. And we'll have to tackle that problem to do a nested model, much finer resolution along the coast, because we're not resolving the barrier islands along the Beaufort Shelf there. And that's where the oil drilling is taking place. BOEM would like to see a model that gets really down to where we can resolve those barrier islands. And we wouldn't be able to afford to run the whole Arctic at that resolution, so we need to do a nested model and figure out how to provide enough conditions from the exterior ice field to the smaller ice patch to make it well behaved.
What happens is she can get numerical instabilities occurring when portions of the model computations are not behaving well. For instance, if you make a water that's too shallow and your currents are going too fast because you've got strong tidal currents, then you can get a numerical instability and try to create predictions of velocities and sea surface height that are so unrealistic, the model dies because it can't handle it. It knows something is so completely out of whack.
The whole system up there is changing a lot. They've We've had talks lately about how just the nature of the pack ice itself has changed from being really solid and thick to being all multi-year ice to being just little patches of multi-year ice with the first-year ice in between. And so it's not as stiff as it used to be. And it's just interesting changes going on. But we will have ice every winter as long as it remains dark up there in the winter, I believe.
We've been flying over the sea ice at fairly low altitude with a helicopter, towing an instrument that allows us to measure the sea ice thickness over fairly large stretches of sea ice, like several hundred miles in total. We do that to be able to look at how thick the ice is on average, but we also look for the thickest ice we can find to look at how that's changing, and so that we can better understand it as a potential hazard that sea ice might pose. When we're flying with a helicopter, the helicopter typically flies at about 100 feet, 30 meters or so above the sea ice. Hanging underneath the helicopter is an instrument that we call an EM bird. The EM stands for electromagnetic, and it uses electromagnetic induction to measure the sea ice thickness. So it emits an electromagnetic field, and that field excites a secondary field in anything conductive nearby. So out in the middle of the Arctic Ocean, 45 feet off the top of the sea ice, the only conductive thing around is the seawater. If the ice is really thick, the ocean is really far away from the bird, and we can measure that. When the ice is really thin, the ocean is effectively closer to the bird, so that the bird measures the position of the bottom of the ice. And then we have a laser mounted on the bird that measures the position of the top of the ice. We subtract those two, the bottom from the top, and we get the total thickness. We don't get a real-time readout of ice thickness as we're flying. There's typically at least two people in addition to the pilot in the helicopter. One person operating the instrument and another person making ice observations, sort of recording what type of ice we're flying over, and other sort of relevant data that allow us to interpret our measurements. We have to wait till we get back and we do some processing of the data before we can really say how thick the ice was. I've been in the co-pilot seat doing the ice observations now for 5 years, and during that time, particularly in the last couple of years, we found it quite hard to find the older multi-year ice that is generally the thicker ice out there. And that's something we expect probably to become more common, is that flying north from Barrow, you have to fly farther and often outside the range of a helicopter to be able to find the older, thicker ice. So our measurements have included more seasonal first-year ice. And you don't actually have to fly a helicopter out there to see that. There's other satellite data that will tell us that. But our measurements, because they give us thickness as well, they allow us to look at changes, interannual variability in the thickness of the first-year ice. And we haven't seen the thickness of the first-year ice change substantially. What we have seen is not only are we finding less of this older multi-year ice, it's not quite as thick as we expect it to be. If you go back 10 years ago and you'd have asked, okay, how thick is the really old ice that passes by Barrow, you might have said, well, 4 or 5 meters thick. And we just don't see anything like that anymore. The really thick ice is 2.5 to 3 meters thick. It is the thickest sort of level ice that we find in the region that we associate with the old multi-year ice. We've been looking for changes over time, but we've also just been trying to better characterize the ice and understand these extreme ice thicknesses and the risks they pose for shipping and engineered structures in the offshore region.
The most important current that connects the North Pacific and the Arctic is the current that flows north through Bering Strait. And that current is enormous. It's like having 50 or 100 Mississippi rivers flowing northward between the Bering Sea and the Chukchi Sea.
On average, there's about 0.8 sphere drips coming in, and a sphere drip is 10 to the 6th cubic meters per second. It's just some big oceanographic unit of water flow. So that's a significant amount of water.
And that's forced by a sea level height difference between the North Pacific and the Arctic Ocean. The North Pacific is about half a meter higher.
So there's a net flow north through Bering Strait. And so we need to provide that as a boundary condition.
Bering Strait is the choke point between the Pacific Ocean and the Arctic Ocean, and it's at a critical juncture for Earth climate processes. It's a really important point for the globe as a whole.
And how wide is the Bering Strait?
About 80 kilometers wide and about 50 meters deep.
So not that deep.
It's not that deep. It's shallow and it's narrow. It's a short little jaunt between Asia and North America there. I'm not a modeler. I'm an observationalist who likes to use the model output. So Kate is the modeler, and she generates these numerical simulations that I combine with my observational data, and I compare against my observational data to make an assessment of how well the model is working.
We can use the model to either prove or disprove some of his theories of what the circulation is doing and why.
Once you have confidence in what the model does, you can use it to fill in those gaps where you don't have actual observations.
And so the role of the computational science is to allow us to build these models to simulate what's going on and so we can look at the model and see the full 3D picture and see it evolve with time as well. And so to help understand what could be happening.
We'll go out there in the summer months, because that's when you can get to these places, deploy moorings, for instance, that are anchored to the bottom, and leave them there. Come back a year later, and with acoustics, trigger a release mechanism, and what happens is the anchor is let go of, the floats on the mooring bring everything up to the surface, and you pick it up, and then you can retrieve your data.
We know that the water fluid motion is described by the Navier-Stokes equations. And those equations have terms such as viscosity, and we call it advection, which is how you carry particle properties along as the water moves. And so you advect things like temperature and salinity and the motion itself. The velocity momentum itself is advected. And there's wind forcing and temperature forcing.
The flow heading northward through Bering Strait into the Arctic Ocean is a first-order contribution to the Arctic Ocean freshwater budget. And that's important because the Pacific water coming through Bering Strait helps to cap the sea ice in the Arctic Ocean from the warm Atlantic water down below. So that helps keep the sea ice on top of the Arctic Ocean. And then the water, which is relatively fresh coming northward through Bering Strait, comes into the Arctic, and eventually it makes its way to the North Atlantic. And the North Atlantic is where the global ocean circulation is primarily modulated from. And that flow can be slowed down with the export of fresh water from the Arctic, a large portion of which originally came from Bering Strait.
So the climate model itself consists of an ocean model, an atmospheric model, an ice model, and a land surface model. Those are the four basic components. So what we're bringing in is a regional ocean model that has to talk to the global ocean model.
So there's a strong connection between the world's ocean currents and what comes through Bering Strait. That's one of the controls on climate that Bering Strait offers for the global weather.
And we're also adding things like ecosystem components. So in the ocean model, it's not just the physical fields. We have different options for running what are called NPZ models, nutrient, phytoplankton, zooplankton. The simplest of those models had just those three components. But the new ones are up, like 12, 15 different components of zooplankton, phytoplankton, and detritus and different limiting nutrients.
There's flow that can happen between the basin and the shelf, all along that shelf. So it's a complicated system, but there are modes of circulation that are preferred for the shelf. And these are driven by the winds, the sea level height difference between the Pacific and the Arctic, and the tides primarily. We had some ideas about how the winds were pushing the waters around, but our analyses more recently have shown that it's much more of an interconnected system than we had thought initially.
Rebecca Woodgate has had a mooring out in the Bering Strait for many years, and Seth took her data and correlated it with the winds, and then from that he could produce an estimate of the Bering Strait through flow. So that's a boundary condition on my model, is how much water's coming in through the Bering Strait. And it is a function of what the winds are doing. The winds can push.
Interesting about Bering Strait is that the winds have the ability to reverse the flow in Bering Strait every once in a while when they blow strongly enough. So if you want to get the circulation right in the Chukchi Sea in a model, you need to be able to get both the standard flow that's forced by the sea surface height difference correct, and you also have to get the wind-driven portion correct. The prevailing winds in the Chukchi Sea are from the northeast, so they're opposing that flow. The flow is usually against the winds. If the winds blow stronger than, say, 15 or 20 knots for long enough, then it could probably reverse the flow.
We watch the ice form in the wintertime. We watch the landfast ice freeze and become stationary. We watch the breakup in the summertime. And we watch all the drifting ice offshore from the landfast ice. And then occasionally, like this year, we actually see a breakout event where ice that would normally be landfast and may actually have people on it detaches from the coast and starts drifting away. That actually did happen just a couple of weeks ago. There were, unfortunately, some whalers on the ice when it broke away. Fortunately, they were able to be rescued. They were able to put a boat in the open water and get out to them and recover them. We have a relatively simple marine radar like you'd find on a fishing boat. We have it mounted to a building in Barrow. It puts us about 20 meters above sea level. And that lets us see sea ice out to a range of just over 6 miles. It's operating 24 hours a day, 365 days a year, except when it has issues, but we aim for continuous operation. Actually, our radar was quite useful for the search and rescue crew in that case because the crew on the ice were able to give their position over the radio. They stayed in radio contact with land this whole time, and they knew they were moving because their GPS was telling them they were moving when they weren't walking around. But with that position from the whaling crew, we were able to plot that position on our radar and be able to tell the search and rescue folks, this is the ice flow that you need to go to. It turns out that information was very useful. In turn, we actually turn to the locals as well for understanding a lot of what we see with the mooring data and the radar. Things happen, ice moves in ways that we don't understand. And we actually have been active in involving local experts, getting their understanding. They're the people who are going out this time of year, not always rescuing people, sometimes they're out hunting in these conditions. And they have their ideas about how the ice and the currents interact and what makes the ice move. We have a very integrated system of observations with technological moorings and radars, but also very fundamental knowledge from people out there living their lives among the sea ice.
An oceanographer asks, where is the water going and how is it getting there? Okay? And that, in particular, is the focus of this project.
How's the ride?
Yep.
So they would throw them into the water, go back home, and the next morning they could look on the web page and see where these 4 drifters are that they had just thrown into the water.
This little ball in here. Those things get bounced around in some pretty big waves, even out in Kuskokwim Bay. And in the winter, when they get out in the Bering Sea here, those things really lead a tough life. So they're pretty well made.
Over the course of 2 field seasons, we had residents of Quinnahock and students from the school system. Quinnahock is a small village on the eastern shore of Kuskokwim Bay. Go out and deploy satellite track drifters in clusters of 4 drifters at a time. And they did this every couple of weeks between June and September.
And when we launched them, these automatically snap out by themselves. We did this in the classroom in the spring on this dummy one, but these are wrapped alongside in this coffin, and when they get in the water there and that coffin goes away, it releases the pressure, and these go popping up and launch themselves in that position.
An important area of the Bering Sea that I think has been overlooked is the nearshore Bering Sea. That region from the coast out to about 60 feet depth of the 20-meter isobath.
An isobath is a line of constant depth, and these typically extend from the southeast towards the northwest across the Bering Sea shelf.
This is where all the fresh water, all the river runoff is first entering the ocean in the Bering Sea side. And there's lots of different rivers that are entering. All the ones around Bristol Bay. Kuskokwim's a major river that's emptying into the Bering Sea shelf. And the Yukon is also a major feed. And in particular, those rivers are important habitats for salmon. And the out-migrating juvenile salmon are all coming down those rivers and eventually entering into the Bering Sea shelf.
Half of our nation's ocean-caught seafood comes from the Bering Sea. The Bering Sea is the home to one of the world's largest fisheries, the pollock fishery, and there's a thriving ecosystem in addition to the huge amount of biomass that's pulled out from pollock alone. There's salmon fisheries, there's subsistence fisheries, there's crab fisheries. So we're interested in the physics behind what drives these productive ecosystems because they're economically important.
Most of the time, oceanographers go out in relatively large vessels, and they can't get inshore. So from a logistics point of view, it's just a difficult place to access.
So there's a big gap of knowledge in that region.
Since we get the data back via satellite almost immediately, we can then display it on the internet, and anyone that's interested, scientists, local folks, researchers in Washington, D.C., school kids in Florida, they can look at that and say, wow, we're understanding something about how the ocean works in this corner of the world.
How long to the first disintegration?
We went into the drifter study thinking naively, as we often do as scientists, that our theories would explain well what these drifters should do. And the theoretical underpinnings that we had told us that fresh water that's discharged from rivers likes to keep the coast on the right-hand side. And so when the river water reaches the ocean, it wants to flow alongshore, and in our case, towards the north, towards Bering Strait. We're seeing the effect of tides, which are these little tiny loop-de-loops that the drifters all do together that gives them the impression that they're dancing. Because the tides are so regular, and then the greater drift towards the west is due to the winds. And there's a little blue dotted line, and that represented a frontal system between the fresh water near shore and the saltier water offshore. And our idea is that the drifters were all held close to shore by this front through the summer months when the winds are weak. But when the winds started to blow more strongly in the fall, that front was broken down, the waters got mixed across it, and the drifters started moving west across the shelf. It's our signal that the fresh water was also moving west across the shelf. That has a lot of implications for the nutrients, the plankton, and the fresh water. And The fate of the fresh water and these nutrients, whether or not they head north into the Arctic or make it towards the Bering Sea Basin, is important for the ecosystem and the climate.
So when we're talking about extreme thicknesses, there's extremely thick level ice. This is ice that hasn't been deformed and piled up into sort of big mountains or ridges of ice. And their extremely thick ice of that kind would be nowadays 4 to 5 meters thick. And we don't really see that so much anymore. One consolidated solid sheet of ice. And that would be a significant obstacle to an icebreaker or a hazard for a fixed structure, like a drill platform or some other structure. The other way that you can get ice thick is to pile it on top of itself. And so you dynamically thicken the ice. And this creates pressure ridges that stick up above the water and they stick down much deeper below the water. And we see pressure ridges that can be, 20, 30 meters thick. And if they're in shallow enough water, then they can actually become grounded on the seafloor and they can gouge the seafloor. And so we've been trying to take measurements over places where we know that they impact the seafloor. Once a ridge becomes grounded, it acts like a traffic jam and more ice can keep piling on. And these things can end up getting very, very thick. One extreme case of this is in a region northwest of Barrow called Hannah Shoal. It's a very biologically productive area. If you go there in summertime, there's likely to be a lot of walrus hanging out in that region because it's a place where ice lingers late in the season. And one reason is because it's very shallow in that region. During the wintertime, these large pieces of ice get grounded, even more ice piles on, and these features become even bigger. They stay there throughout the summer because they can't drift away because they're sitting on the seafloor. So they're very important for walrus as a haul out. But once they do break up from the seafloor, once they do sort of melt sufficiently to where they can uplift, well, then they potentially become a marine hazard. So the ice that caused Shell to stop drilling after they'd only been drilling for 1 day in 2012, that ice likely came from the Hannah Shoal region. As a result, there were probably parts of that ice that were very, very thick, that have been sort of thickened by this dynamic ridging process. And so Hannah Shoal is outside the range of a helicopter from Barrow, so we've only been able to get 1 year of data over Hannah Shoal when we had this fixed-wing aircraft with a longer range. But there's other features closer to shore that are like mini Hannah Shoals where we can look at this process, and we've been trying to measure ice thickness in those regions as well. One, to improve our ability of how to measure ice that thick, because that's not a trivial matter either. And two, so that we can look at how they form, how often they form, and how thick they get.